next talk is Equivalence and Similarity Refutation for Probabilistic Programs, and our speaker is Ehsan Goharshady. And hopefully we can get the slides up. Yes, there we go.
Okay. Hello everyone, welcome to my talk on Equivalence and Similarity Refutation for Probabilistic Programs. I'm Ehsan Goharshady, and this is a joint work with Krishnendu, Chatterjee, Petr, Novotný, and Đorđe Žikelić. So to first introduce our problem, consider the following two programs. The program on the left is trying to send 8 million messages to the other side with failure probability of 1/1000. And the program to the right is trying to send 9 million messages with failure probability of 1/2000. Now, obviously, these two probabilistic programs do not yield the same output distribution after being executed. This is what we mean by these two programs not being equivalent. So when we execute the programs, the output distributions are not the same. And now an interesting question is, given two probabilistic programs, can we prove them to actually not have the same output distribution? And as opposed to non-probabilistic programs, this is a very hard problem because given two non-probabilistic programs, we can simply run them, get the output, and see if the outputs are not the same. But when thinking of probabilistic programs, we need to actually think of these distributions, and reasoning about distributions is much harder. Furthermore, we are also interested in saying, okay, if the programs are not equivalent, then how far apart are they? What is the distance between the distributions that they actually return? To motivate this problem, we can consider two implementations of the same randomized algorithm, for example, where we want them to actually return the same distribution. So it's really important to actually check for, this is actually a way of checking for bugs, for example. Another motivation could be these sampling methods, where these are very familiar, these are very popularized now in the AI and ML community, where they are sampling from a distribution, and now we really need to make sure that the distribution is actually correct in the sampling algorithm. Another very important way to use this is for checking if the probabilistic program compilers are actually doing the right thing, if the compiled program has the same distribution as the actual program. So these all show that actually verification and refutation of equivalence are really important. To now define formally what I mean, consider two probabilistic programs C1 and C2. We say C1 and C2 are output equivalent if for any measurable set B in the possible set of outputs, the density of B in the first program and the second program after termination is the same. And now the equivalence refutation problem asks, given two programs C1 and C2, prove that they are actually not output equivalent. There has been a lot of previous works related to these problems. I'm going to summarize them here. The first class are logical frameworks which are not automated. The second class are methods that actually only consider finite state probabilistic systems. But in the case of programs, we are also very interested in programs with real valued variables, which means we actually need to deal with infinite state programs. And the third class are statistical methods, where they basically sample traces of the program, and then they try to think and infer non-equivalence of programs based on their samples. However, these methods do not have very strong guarantees on the results, so they cannot say for sure that these two programs are not equivalent because they only can see some finite number of traces. And also they don't scale well when the running time of the programs is huge, because they still need to take a lot of samples, and each sample might be large on itself. Our method, on the other hand, is the first one, which is fully automated. It supports infinite state programs with real valued variables. It has formal guarantees on its results, and it's a static analysis method, which means it actually does not depend on the running time of the program. All right, so I'm now going to dive into our proof rule for disproving equivalence. Our proof rule on a high level is basically searching for a function f from the possible set of outputs of the program to the reals, where the expected value of f upon termination in the first program is not the same as the expected value of f upon termination in the second program. Equivalently, we can only search for a function f where the expected value in the first program is less than the second program. And this means we can also only look for an upper bound for the expected value of f in the first program, which is less than the expected value of f in the second program. In the paper, we show that this is actually a sound and complete proof rule for disproving equivalence. So if two probabilistic programs are really not equivalent, such a proof rule for them has to exist. Now for the upper bound part, so now our goal is to basically find this upper bound and the lower bound. For the upper bound part, we introduce the notion of upper expectation supermartingales, or for short UESMs, which is a function from the states of the program to real variables. And it should satisfy two conditions. First, it should be 0 on output, so on every reachable termination location, its value has to be 0. And second, it has to satisfy an expected f decrease condition, which means for every state S of the program, the difference between the current value of u and the expected next value of u should be greater than the change in function f. Now, intuitively speaking, this function u at each state S will be an upper bound on the expected difference between the current value of f at that state S and the value of f upon termination, which means specifically in the initial state of the program, the sum of u and f will be an upper bound on the value of f upon termination of the program. So by having a UESM, we have an upper bound for the value of f at termination. Similarly, for lower bounds, we introduce the notion of lower expectation submartingales, which is again a function from states of a program to the reals. It should be 0 on output, but here it should satisfy an expected f increase condition, which means the expected difference in the value of L should be less than or equal to the expected difference in the value of f. Then again, intuitively speaking, L at each state S will be a lower bound on the expected difference between the current value of f and the value of f upon termination. So in the initial state, the sum of L and f will be a lower bound for the value of f at the end. So our complete proof rule will look something like this. A function f from the possible outputs to the reals, a UESM u for the first program, an LESM L for the second program, such that the sum of the u and f in the first program is less than the sum of L and f in the second program, which means the upper bound we have for f is less than the lower bound for f in the second program. In the paper, we show 4 conditions where under each of them, this proof rule will actually be sound for disproving equivalence. First one is if the program has statically bounded termination time. So if there is some number n where we can say the program is definitely terminating after n steps. Secondly is if the program has statically bounded variables, which means all variables are bounded from above and from below. There are also 2 other conditions which are complex, and I'm not presenting them here for the sake of time. Algorithmically speaking, we also come up with a template space synthesis algorithm for finding these proof rules. It has 4 steps. The first step is basically fixing a symbolic template for all the parts of our proof rule for the function f, the UESM u, and the LESM L. Then we collect their defining constraints, which are of the form, okay, there exists some valuation of a template variables such that if some condition is satisfied, something else should be satisfied. Just trust me, they look like this. Then we use Handelman's theorem from algebraic geometry to convert these exist for all conditions into purely existential linear constraints. And then we simply solve the linear constraints with the added constraint that the sum of u and f at the initial state in the first program should be less than the second program. For example, consider the first program that I showed. We first fix these templates for the functions f, u, and l. So here you can see that we put the template S1 plus S2 fail plus S3 send, where S1, S2, and S3 are unknown template variables. We are looking for valuations of this S1, S2, S3, and also these C variables for U and D variables for L. We are looking for evaluation of these variables such that it satisfies the 0 on output and the F increase, F decrease conditions. Now, applying our algorithm and feeding the linear program to a solver like Urobi, we obtain this witness for this program. which basically means that the expected value of sent minus fail in the first program is different, or is basically less than the value of sent minus fail in the second program. So in the title, we were also talking about similarity, which is basically how far are these two programs from each other. So the problem that we consider here is, given two programs C1 and C2, we want to find the contour-which distance between their output distributions. We want to find a lower bound here to be at least epsilon. And in the paper, we have come up with a similar proof rule for refuting similarity. And we have also come up with a very similar algorithm to make it fully automated. So if you're interested, you can read our paper. Experimentally speaking, we have gathered 18 loopy programs from the program analysis literature. And as a baseline, we consider a combination of PSI and Mathematica. PSI, as mentioned before, is a symbolic integration method, which, given a probabilistic program, it outputs the exact distribution of its outputs. And what we do here is, given two probabilistic programs that we want to prove that they're not equivalent, we feed both of them to PSI, we get their output distributions, and then we give these distributions to Mathematica and ask Mathematica to prove that they are not actually the same distributions. However, PSI only supports statically bounded loops, which is why we had to we had to modify our benchmarks to have loop lengths of lengths 10, 100, and 1000. So we had 18 original benchmarks, and we also have these 3 modifications. We have 72 benchmarks in total. Here is a summary of our experimental results. As you can see, our method can successfully disprove equivalence in almost all the benchmarks, where PSI disproves a lot less. And also our method can find lower bound on the contour-which distance of the two programs in almost all cases. And also, you can also check how the times our algorithm is very fast, actually. Here is the rest of the experiments that we did, and you can still see that our algorithm can successfully refute equivalence in actually all benchmarks, while also finding a lower bound on the contour-which distance. All right, to sum up, we came up with the first static analysis method for disproving equivalence and similarity of programs, which is fully automated, has formal guarantees on its results, supports infinite state programs, and does not depend on the length of a program executions. And as future works, we are thinking of extending this method to programs with conditioning and observation statements. We already have some preliminary results, but we are still thinking about this. And another very important extension is to extend this to non-polynomial UESM and LESM. So basically, the algorithm that I showed, because we use these theorems from algebraic geometry, we can only look for polynomial witnesses. However, other algorithms to actually consider non-polynomial UESM and LESMs will also be very interesting. To this end, I will look to conclude, and I will be happy to answer your questions.
Let's thank our speaker.
Thank you for the great talk. One question I have is, you said the programs need to satisfy a set of conditions for the soundness to hold. You didn't show all of them. Some of them were more complicated. Can you give a sense how feasible it is to check these conditions from the source code of a program?
So most of them, I would say, can be checked statically again on the program. So for example, checking if a program has statically bounded termination time. There are many methods for proving termination of programs, so they can all be used. Also for statically bounded variables, I think this can be shown as a sort of invariant on the programs. And the third and the fourth method are also, the conditions, they are also pretty much, there are various methods for checking them. That's why we really did not consider checking them here.
Okay.
But
good.
Yes.
Yeah, and just briefly a second question. Your method searches for polynomial certificates. So do you start with degree 1, degree 2, degree 3, and you're doing a search in that way?
Yes, exactly. So I summarized that part, but the idea is exactly we start with degree 1 polynomials. If we found something, then that's great. If we didn't, we go to degree 2 and then degree 3.
Okay, good.
Yeah.
Thank you.
Okay, thank you for a great talk. I have a question. I see the proof rule you provide is sound but not very complete. And I would like to know when the two programs are very close, are your proof rules are enough to resolve this question? Sometimes like the probabilistic parameters is very close, like in this situation, I would like to know your proof rule is enough to resolve.
Yes, so even in our experimental evaluation, I think we had benchmarks where, for example, this Bitcoin mining, the distance between the programs is very small. It's like 0.005, but still our method can find this, because one thing about this equivalence refutation witness that we have is that you can multiply this function f by any constant, by any positive constant, and it will still, and you can basically multiply the whole witness by a positive constant. And it will still satisfy all the conditions. This means even if the distances are very small, you can come up with functions with big enough coefficients such that a solver like Roby can still find it.
Maybe another question is that I would like to know, have you considered the polynomial template? Because I think it's the linear template you use and use the Handelman theorem. Maybe in the polynomial templates case, the Putnam theorem can be used to resolve the template.
Yes, so we also considered polynomial templates, and for polynomials we used Handelman's.
Yeah, I know the Handelman is not enough to resolve the polynomial case.
No, but because in this case, so we can also talk about this offline, but the left-hand side of our constraints are usually linear expressions, and the right-hand side are polynomials. So that's why we can use Handelman, and it still stays sound and complete in this sense.
Okay, thank you.
All right, thank you much.
So I have one question. So can your similarity refutation works also for refuting coupling properties?
What do you mean by coupling properties?
I mean, there is a coupling between two programs so that their outcome distribution are close.
I think they should be able to. We should be able to use them for that too. Yes.
Okay. Thank you.
All right.